Yes, I can.
Are you speaking?
Yes. Can you not hear? Hello?
Okay, can you type in if you can hear me? Um, Maybe my speaker is, I think our speaker is working. It's your mic problem. Okay, now that you confirm you can hear me, let's get started. So I have a question slash proposal to run by the class, which is the topic on partial differential equations involves a few concepts and Fourier series. You can't do partial differential equations without doing Fourier series. Okay. The one aspect of Fourier series which I think is really important, but I don't really test you or kind of give practice on, is discrete Fourier transforms. Because when you're in the lab, you collect data. When you have to run FFT on that or a DFT on that, that is the important way in which you use Fourier transforms in a practical way. So I came up with this idea. Tell me what do you think? The exam 2 is supposed to have at the moment 4 questions, 80 minutes. Instead of that, what I think we could have is 3 questions on only PDEs for 80 minutes. So the weightage of the exam will also be reduced from 20% to 15%. The other 5%, I can give you a programming assignment where your only task is to develop a program in which you calculate the DFT of an arbitrary signal. You'll be given an array of time series data. It has to take that as the input and output the Fourier transform of that series of data. It's essentially implementing, I think, equation 18 of the book as a computer code. That'd be interesting. I know with your turbulence, you can get some velocity fluctuation and get the frequency content of that with your control systems. Ayush, you could do that as well. Anyone who has access to an oscilloscope can get data. So you can get your own data, run it with your program, and get a DFT of that. How about that?
Good thing because I think that when you program something, you get to know everything.
Correct. So is everybody up for this? 5% for this mini project. All you have to do is develop a program which implements discrete Fourier transform. It's given in the book. The equations are there. How to discretize the frequency space, how to numerically compute the Fourier transform at each frequency. All the equations are there in the book. All you have to do is implement that as a MATLAB code. And if you don't have access to a lab and you don't have signal, you could get signal or data from one of your friends. Like you can run an oscilloscope data and give us voltage time series. Or maybe you can come to my lab and you can get an oscilloscope data, which you can run oscilloscope data, can't you? And you can get a few data sets and share it with the rest of the class. And whoever has access to their own experimental facility, you can bring your own data and do a DFT on your data and show what frequency content is there. Is everybody cool with this?
So, when do you plan on the deadlines for it?
I was thinking a week after second exam. So on October 30th is when you turn in your first project. November 4th is the second exam. So you'll all be frantically studying for the PDEs for second exam. And maybe a week after that, if I make this assignment due, you get 1 week to write a program with one for loop. How about that?
Yeah.
Right? The for loop at the end of it. It's just 2 equations and a for loop. That's it.
But the exam will be 80 minutes still.
Sorry?
Even with the 3 problems.
3 problems, 80 minutes. And PDEs is such that 3 problems can keep you busy for nearly 80-90 minutes. You're slightly given more time, but I don't think that's okay. I think you'll need it.
I think it's incorrect to answer 3 questions in 80 minutes of PDs.
Sorry, I've stopped negotiating. It was never a negotiation. I'm just giving you my proposal.
Yeah, that's good.
Are you up to doing this DFT exercise?
We'll do that fetch and if Fourier series probably not the question, that's right.
No Fourier series, direct question, but like I said, you can't do PDEs without doing Fourier series. So in fact, I thought of a template for the exam. There is going to be one-dimensional Cartesian coordinate wave equation, one like a Laplace equation in cylindrical form, and then one spherical polar equation. In fact, I can tell you what the three types of equations will be, and we can come up with so many combinations of boundary conditions to give you some challenges. So 3 problems on PDEs, that is the exam, and the FFT is the mini project. Okay, and it will be due around November 6th or 8th, something like that. 1 week after the first exam. Okay? Okay.
Next Monday. Download.
Yeah, whenever the exam is, the following Monday. Okay? And remember in November, you also should put time into your second project, which you will present at the end of the course. That second project is something I will talk about once I'm closer to finishing PDEs, because I have examples from past years where students did projects, and what they basically did is to pick up a problem which involves solving a PDE, set up the problem, write down the boundary conditions, and then actually solve it and discuss the solution in front of an audience. So sort of like a research presentation. Okay. All right. Good. Now that I also have your cooperation, I almost rewritten the syllabus. I'll post it tonight. Okay. Okay. So today, what I wish to do is I could start PDEs right today, or I could spend a little more time doing examples on Fourier series before we get into that, just to get some integration practice and get our the blood flowing. Sorry, practice. Yeah, Fourier series practice. Okay. So that is what we'll try today. We'll start with writing conventional Fourier series in terms of trigonometric functions, which you can go back to the first topic that we discussed, which is section 11.1 and 11.2. So let's pick out a couple of examples in that. If you have already attempted problems and you have something that you would like to try, please suggest. Okay. So I'm talking problem set 11.1 and 11.2. The only difference is in 11.1, the interval is -pi to pi or 0 to 2 pi. And in here, the interval is arbitrary. So let's try this. Unless there is a suggestion or something you want me to try, I'm going to suggest problem set 11.2. Problem 8. So here is f of x given to you in this graphical form. Here is -1 to +1, and y equal to -x for x less than -1, x less than 0, and y equal to x for x greater than 0, which you can compactly write f of x equal to absolute value of x, and x varies between -1 to +1, or -L to +L. Let's represent as a Fourier series where we write f of x equal to a0 plus sigma n equals 1 to infinity an cos n pi x over L plus bn sin n pi x over L. I know this is sometimes even below your level, beneath you to do such a simple problem, but this is just to get the legs moving, okay? All right, so A naught, as you know, is 1 over 2L minus 1 to 1 f of x dx or minus L to L f of x dx. One useful tip is always look if the function is odd or even. That will allow for you to quickly do simplifications. In this case, is this function odd or even? This is an even function, okay? So if you also think about the other two coefficients, an 1 over 2L minus L to L f of x cos n pi x over L dx. This is an even function, this is an even function, that's good. But if you look at Bn is 1 over 2L minus L to L f of x sine n pi x over L dx. Our f of x here is even, but sine x is always odd. So you can almost write it without anything else, that Bn is 0. A useful simplification. Okay, Bn is 0. A naught is 1 over 2L, 2 times 0 to L, f of x dx, which is 1 over L, 0 to L. In our case, this is absolute value of x. Between 0 to L, this is just x dx. So this is L squared over 2L or L over 2, which is 1 over 2. An 1 over 2L, 2 times 0 to L, x times cos n pi x over L dx. How many of you don't have access to a textbook, like a paper copy? So many people don't have access.
Library has not previous edition.
Okay, so how do you do practice problems?
The periods of PDF.
Okay, so if I allow you to bring 2 sheets of notes and any number of sheets that have tables of series or integrals, would that be okay? I'm okay to even letting all of you bring a book, but since some of you don't have the book, it will be a problem, like become unfair. So you can bring 2 sheets of handwritten notes and printed material containing tables of integrals, series, such kind of stuff. Okay. All right, you need to complete this. Please do and tell me the answer. One second. Yes.
Shouldn't it be 1 over L in AN?
Here. Yes. 1 over. I forget.
I think 1 over 12 from price which is.
Okay. Yeah, I guess you're right. Yeah. Yeah, 1 over L. Right. So let's complete this integration. So I have 1 over 2 over L. L over n pi minus cos n pi over L. So, U over L, L over N pi, and L over pi. I have cos N pi minus 1. Cos N pi minus 1. Get 2 over N pi minus 2 over N pi 1 plus cos N pi minus 1. This is minus 1 power N plus 1 times 2 divided by N pi. Am I correct? Did I miss something? So our Fourier series going to be f of x equal to 1/2 plus summation n equals 1 to infinity minus 1 power n plus 1 times 2 divided by n pi cos n pi x. Since L equals 1, or this is 1/2, I write this as minus 1 power n, make this a negative sign, minus here. Minus 2 over pi. I have cos pi x or minus cos pi x over 1 plus cos 2 pi x over 2 minus and so on up. You have to tell me if I missed something. And usually a problem like this will also say, using this result, determine sigma 1 over n, where n runs from 1 to infinity.
Yeah, we will integrate sine of n pi x by n. And we will get another term of n pi by n. So there should be cos of
Oh, yeah.
cos of n pi by L divided by n pi by n
So
square.
L squared by n squared pi squared, right? So I have to go back here, fix this. So this goes away, that we are clear. And
Here is a minus of n point.
okay, let me just redo this. So up to here we are okay, right? So I have 2 minus 2 over n pi 0 to L sine n pi x over L dx. Okay, so then this is minus 2 over n pi minus cos n pi x over L divided by n pi over L from 0 to L. So if I do some simplification right here, this is 2 L divided by n squared pi squared. Upper limit is cos n pi, lower limit is 1. So this is 2L divided by n squared pi squared times minus 1 power n minus 1. So all even values of an are 0. even values vanish. So I have half plus sigma n equals 1 to infinity plus 2L divided by pi squared times minus 1 power n minus 1 divided by n squared cos n pi x, which I can rewrite n equals 2m, that is only even values of odd values of n. So I'll write 2m minus 1. So f of x equal to 1 by 2 plus 2L over pi squared sigma m equals 1 to infinity. This is minus 1 and minus 1. So this is automatically minus 2 divided by 2m minus 1 whole squared cos 2m minus 1 pi x. So I can rewrite minus 4L cos 2m minus 1 times pi x. So just to use this result, if I substitute x equal to 0 on both sides, f of 0, which is 0, f of 0 is 0, 0 equals 1 by 2 minus 4 by pi squared times this cos 0 is 1 times 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus and so on up to infinity. So I would get summation or the values of this series 1 plus 1 over 3 squared plus 1 over 5 squared plus and so on is equal to pi squared over 8. That is one of the utilities of this type of representation is to evaluate such infinite series. And this is an important point that you substitute x equal to 0 because x equal to 0 is contained in this interval. You can't just directly substitute some random value outside this interval. It has to be within this interval.
What does pi squared over 8 represent in the function?
Sorry?
What does pi squared over 8 represent like in the function?
I'm not sure about that, but what I know is that if you can evaluate the function and also its Fourier representation, it can be used to evaluate certain special series. What were you going to say?
X is equal to 0, it is the value of.
The value, yeah, that's what it's. Yeah.
So like from this series, we can calculate the value of pi.
Yes, if you can numerically compute, this is one way to also check the value of pi. So you can use this to calculate pi, or if you treat the pi as the known, you can use it to calculate special series. Sometimes you might get a pattern that is much more complicated than this, just this. So you might be able to do infinite series summation. So the kind of questions that you can expect is a function that is provided to you on a finite interval and representing that as a Fourier series. Of course, like I just said, we are not going to have separate questions on Fourier series, but this is something we will use when we do partial differential equation. But because how it will fit in there is to write one possible solution, yn of x is of the form something like arbitrary constant times cos n pi x over L. So then we'll write the entire solution is any values of n can be included, which then becomes a Fourier series, which we'll soon see perhaps even in the next lecture. So the complexity really lies, or the work really lies in the type of function that is given to you and you carrying out integration. Okay. Again, feel free to bring any tables of integrals, and I don't want complaints that integration took too much time. Bring whatever you want, okay? All right, the other major or second major concept in this topic is that of orthogonal functions. I'll do a very quick recap. Orthogonal functions. Ym of x and yn of x are orthogonal in the range a less than or x less than or equal to b if and only if integral a to b ym of x, yn of x, r of x dx is 0 for m not equal to n and a finite value for m equal to n. R of x is called is the weighting function, usually a positive function. Not usually, R of x is a positive function in that interval. Okay. And typically we write, and also I should define the norm. The norm of ym of x squared is equal to a to b ym of x squared r of x dx. So a type of question possible here is proving the orthogonality of a given class of functions. Like for example, either trigonometric functions sine mx or m pi x, cos m pi x, Legendre polynomial of order m, where m is an integer. Maybe to denote that, I'll say pm of x, and then Bessel functions jm of x. So proving the orthogonality of these is a way to is one of the question types we can think of. Of course, outside the exam, what is the use of proving this orthogonality? Forget the exam for a second. Why would you want to prove the orthogonality of a class of functions?
So you can use them as basis functions.
Good. So you can represent any given function as an infinite series of a naught ym of x, okay, A naught ym of x in an interval x between A to B, in which ym of x is orthogonal. If they are not orthogonal, you cannot use them as basis functions. Okay, so proving orthogonality is the first step towards representing a given function using ym of x. And this we call generalized Fourier series. This is section 11.6. Although I've ruled out asking a direct question on like this on the exam, you will need this again when we do cylindrical and spherical partial differential equations. So if you represent f of x in this form, right, am will be a to b ym of x squared times r of x dx, like y of x times r of x times f of x dx divided by the norm of the function, which is a to b ym of x squared r of x. Okay. So we did, I think, one example on Fourier Legendre series. Let me pick out something from the problem set and we'll try that. Okay. I think we did x squared for Fourier Legendre series, and let's try something else. All right, so I want to try this example. Can I, is this okay? Are people still writing this? Good. Wait first. So let's try a simple function f of x equal to sine pi x, and you want to represent that as summation m equals 0 to infinity am pm of x in the interval -1 to +1. So for reference, the Legendre polynomial of order n, okay, order n is m equal to 0 to uppercase m -1 power m. Of course, nobody might not remember all the Legendre functions, so I'm just giving you the general formula. Two n minus 2m factorial divided by 2 power n m factorial n minus n factorial n minus 2m factorial x power n minus 2m, where uppercase m equal to n by 2 if n is even, and n minus 1 divided by 2 if n is odd. This is something I would put on the exam. Maybe you would also have on your sheet. Okay. All right. Where do you begin? You look at this functional form and this, if our ym of x happens to be the Legendre's polynomial, we also take r of x equal to 1. Okay, this is the starting point. You don't know at this point, or at least it's not explicitly told, that whether this function is orthogonal or not in the given interval. We have to establish that. Okay. Of course, when we do the integration, you're going to find out it is, but instead of doing it, can you please tell me what exactly you will check for? How will you prove this? That this is orthogonal in this interval. Right here. You want to take two different integers m and n. You want to plug in this function and carry out the integration to show it. It looks pretty messy because this is a infinite summation. I'm sorry, not infinite summation. This is a summation with several terms. And if you choose m and n to be arbitrary, the symbols can get out of control. Right? So one way to do this is just to try for a few values and show that they are on the right track and make some generalizations from there, instead of handling this ugly summation within this interval. So for example, you can try P0 and P1 and see if they are actually orthogonal. Can we just check that as a sample? So consider P0 of x and P1 of x. This is in the interval -1 to +1. So that would be -1 to 1. P0 of x. What is P0 of x? 1. You can look that up. The first few Bessel functions are really simple functions. P0 of x is 1. And P1 of x is x. So really simple, 1 times x dx, which is obviously 0. You don't even, it's an odd function. You can try P0 of x and P2 of x. This will be -1 to 1. What is P0? 1. What is P2? Is it x squared minus 2 or 3x squared minus 1? Minus 1, right? Half of 3x squared minus 1. Half of 3x squared minus 1 dx. Okay, so this is the even function. So this is half times 2 times 0 to 1, 3x squared minus 1 dx. So this is 0 to 1, 3x squared is x cubed. So 1 minus 1 equal to 0. So you can prove many of these by like trial and error, or trial and error, sorry, trying it for specific values of m and n instead of trying to handle the whole beast. All right, assuming that we have established fully that this Legendre polynomial is in fact orthogonal, we need to apply this formula to calculate AM in general and try to simplify that as much as possible. So AM would be -1 to 1 PM of x squared times sine pi x dx divided by -1 to 1 PM of x squared dx. At least getting the first 3 or 4 would give you the coefficients, and if you're doing a computer program, these are the values, AM values are the ones that you want to program in, right? Like a generalization for AM. Okay, so where do you want to start? Do you want to try with this, or shall we try specific values? I would say specific values. Okay, so what is A0? -1 to 1. PM of x is 1 squared sine pi x dx divided by -1 to 1 squared dx. This is the odd function, so this is 0. P0, P2 and P4, all even values are going to be zeros, right? Because if you write out the Legendre's polynomial, P0 of x is 1, P2 of x is half 3x squared minus 1. What is P4 of x, if I can look up and write? P4 is x power 4, that is 1 over 8, 35 x to the 4th minus 30x squared plus 3. So P2m of x contains only even powers. Contains only 2m or x power 2m, x power 2m minus 2 all the way to x power c. So a useful simplification is A2m is 0. You're okay with it? Are you okay with it? Yeah, yes, possible. So A2m is 0. Let's look at what is the odd functions or odd coefficients, A1, A3 and so on. A1 is -1 to 1 x squared sine pi x dx divided by -1 to 1 x squared dx. Now, when you later evaluate these coefficients as part of a solution to a PDE, and you would be developing a program for your project, what would be handy to have is a numerical integration routine, like a Simpson's 1/3 rule or trapezoidal rule, that you can just call and pass the function as well as the limits and get you a numerical answer. Each time I don't expect you to do the integration analytically and punch in the formula into the program. It should just use numerical integration. And this is where in an exam, this can get tricky. If you have this as a formula ready made, it will be easier for you, save time. Okay? So how do we do this integration? Should we do this? Can you handle this later? Like in the sense so that I can cover one more example. Okay, so you can handle this. So A1 is going to be a numerical value, something that you can get with your calculator. And similarly, there will be A3, which will be -1 to 1. The function P3 happens to be half 5x cubed minus 3x. This is half 5x cubed minus 3x, and I have to square it, times sine pi x, and the whole thing divided by -1 to 1 half 5x cubed minus 3x, the whole squared dx. Yes.
Like, if there is a limit, like when we are calculating the A1, like, do we need to really show the calculation or we can just use the calculator? If there is limit and it is simple.
Yeah. You don't have to show the steps. If your calculator has this capability and you can write the answer, that's fine with me. The only question is, do all of you have access to such calculators? Because I haven't used one in like 10, 15 years. I use only MATLABs.
And pi of x is the main order function. So
Sorry,
is it
This
yes?
this is 0.
yes.
It's the order function.
Right. This is 0. Is this also 0? Hopefully not.
Maybe it's the same of pi.
No, this is not a odd function. This is squared. So this is not an odd function, but this is a odd function, correct? So we are getting everything to be 0. That can't be right. This is even. This is odd.
This is also 0.
Okay. Did we then get the other thing right? That is when we do the anyway, to your question, yes, you can use numerical integration. We'll talk about calculators later. Everything can't be 0. What are we missing? Oh, that's because not because of the function. It's because of my writing. This is y of x times f of x. This is ym squared. This is the norm. There is no square here. Now it will not be 0. In fact, the answers to this particular example is also discussed as an example in the book, which happens to be example 1. Right? Example 1. Yep. Under example 1, you can find the values of A1, A3, and so on. A1 happens to be 0.9549. And A3 happens to be minus 1.1582. And you can compute others and verify A5, A7, and so on. This is in page 505 and 506. Okay. Okay. For the same function, can you represent this as a Fourier Bessel series of the form m equals 0 to infinity am jm of x? First of all, tell me this, the value of am in this case and the value of am in this case, are they the same values, same ams we are talking about, or what are these ams? Think of this function kind of like a target that you want to build, like a picture you want to build. These basis functions are like building blocks, like Lego blocks. If you buy Lego blocks from brand one, they have different sizes and different say dimensions. The dimensions and different ways they mate with each other. When you have the Legendre polynomials, these coefficients are the necessary amplitudes or weights with which you have to combine those functions to get a targeted function. The same logic applies if your weighting function or your Lego blocks change, you have them with different dimensions now. So you need different numbers of those to form the same function. Okay, so they are weightages which will change with the nature of the function that is used. Okay, so it's a very simple adjustment that you are using Bessel functions now as the basis. The way you calculate it will remain exactly same. Only thing that will change is the values themselves. Okay. So when we encounter partial differential equations in spherical polar, we end up with a Legendre's equation. The solution will look like this. When we encounter in polar or cylindrical, it will end up being a Bessel's equation. That is where representing the same function that appears as a boundary condition as an infinite series becomes useful to us. Okay, so let's complete this so that in some remaining time, I can maybe even think of discussing the first type of PDEs. So if you're wondering what is the Bessel functions of order n, I can write it out. Unlike Legendre polynomials, Bessel functions happen to be infinite series. So we want to write Jn of x equal to m equals 0 to infinity minus 1 power m x power 2m plus n divided by 2 power 2m plus n times m factorial m plus n factorial. So you can get J0, J1 and so on and so forth. So what is the properties of these functions? If you say J0 of x, that is m equals 0 to infinity minus 1 power m x power 2m 2 power 2m m factorial squared. What can you say about J naught? Even function, right? It's an observation that it's an even function. And J1 of x will be an odd function. So m equals 0 to infinity minus 1 power m, 2 power, x power 2m plus 1 divided by 2 power 2m plus 1 m factorial m plus 1 factorial. So these are odd functions. And you can easily say in general, J2n of x is even and J2n plus 1 of x is odd. So when you have this kind of odd and even combination, what's the first thing you will look for? In your given function, you will try to identify if itself is an odd or even function, right? Because that will simplify some things. Because sine pi x is odd, you have a m equal to minus 1 to 1 jm of x times sine pi x dx divided by minus 1 to 1 jm of x squared dx. So this is odd. If this function is even, this integral is 0. Right? So this implies a 2m is 0. Because all 2m's are even, so this will make this coefficient 0. Okay. And then if we consider odd functions, that is odd values, we have a 2m plus 1 or 2m minus 1, either is fine, minus 1 to 1 j2m plus 1 of x squared sine pi x dx divided by this is where having a good numerical integration routine ready will save time for you. Okay, so for example, A1 is minus 1 to 1 J1 of x sine pi x dx divided by minus 1 to 1 J1 of x squared. So you are in the exam, you have this integral in front of you. If you don't have a calculator that can do integration for you, what exactly would you do to get the work done? Complain to me that the exam is too long. That's the strategy.
I'll read the common patterns.
Sorry,
For me, I would read the common patterns in
common factors,
common patterns.
common patterns. Okay, I mean, I'm just asking, let's say, I ask you for the representation and I say it's sufficient if you compute the first 3 non-zero coefficients. I'll say that in the problem statement. You don't need to go for a pattern, which you are welcome to, but if I just say something practical. Get me the first 3 coefficients or first 6 coefficients, not 6. In the exam, I won't ask 6, but in reality, you write a for loop. It computes the first 10 terms or the first 6, first significant terms and stops after a while. So how do you evaluate this in the exam is my question. You all know the answer. You just have to think back to your undergrad days. You have done computation or numerical methods or introduction to programming, something you would have done. So how do you get an answer? You can't get the exact answer to this by evaluating everything to the dot. I would go for the next best. What is the next best? We already did that. We are here. You can write it 0 to 1. That won't change much now. It won't simplify your complexity much. And maybe it will give you a 0 as the lower limit, which might help you discard the lower, but you still have to do the integration. That effort doesn't change. The whole problem here is this is a brute summation that is an infinite series, and here's a function. So if you multiply this function inside, you are going to get x sine x, x squared sine x, x squared sine x, x to the 4th sine x, or something like that, or x sine x, x cubed sine x, and so on. Who has the time to do so many integrations? What will you do? Practically think, say something.
Guys, values between -1 and 1, we can.
You want to write like 10 values, evaluate the function at 10. You basically want to do numerical integration by manually. Okay, all right. Any other ideas? Yeah,
I was making the exam, I believe I it is.
and accept the 20% credit. That's a choice. I'm not actually sitting there with an answer with 4 decimal points, and if you don't get it, I'm not going to be talking points. I'm looking for your thinking, your approach. How will you solve this problem? Give me some strategies. You will get 20% for your strategy.
We can calculate J1 as 1 and simplify the integration.
Wait, J1 you want to approximate as 1?
No, J1 of 1 when x equals 1. Because
So you want to write this is like A1 equals J1 of 1 sine pi minus J1 of -1 sine pi. Is that what you want to do?
no, since the integration is even, we can do the integration from 0 to 1,
Sure.
and then the value at 0 is 0. So we would have to calculate the value at 1 only.
But this is sine pi.
Oh, yeah.
But at least you've got some thinking going. Can you think for the times clicking?
I have another idea.
Yeah.
What if we just approximate for the first factor of the series?
First factor means how many, like what are you talking environment?
Not different, but just one.
So you want to just include the first term? Yeah, think a little bit, 40%.
I mean, the first term is the one that contains the most information, right?
Yeah, but the second still contains enough information that you can't discard it. Maybe the sixth is not important, but second term still has something. Third term, even less something, but still something. So what are you getting at?
It will be easier.
You are saying approximate J1 of X approximated as the first three terms instead of an infinite series, because it's a series which decays pretty quickly. There's a huge term on the denominator. Later coefficients will quickly go to zero. So you can say this J1 of X, only the first three terms make up most of the value. The later terms count for less. Thanks for not saying that. But J1 of X can be approximated as what? It will be X. First term is X. So I have M equal to 0. 1 over 2 times 0 factorial, 1 factorial. So 1 over 2. What is the second term? M equals 1. Minus x squared divided by 2 power 2m, which is actually I can write this half outside. 2 squared is 4. 2 power 2m. 2 squared is 4. 4 times 2 factorial is 4 times 2 is 8. So x squared over 8. Third term is plus m equals 2. M equals 2 will be x to the 4 divided by 2 power 4 is 16. 16 times 2 is 32. 32 times 6 is 8. 32 into 6. 19. Yeah, 192. 192. You can meaningfully say you are approximating J1 to be this function. And you still have sine pi x, which if you multiply, you will end up with sine pi x, x cube pi x, and so on and so forth. So you can write sine pi x is represented as pi x minus pi squared x squared over 3 factorial plus pi cube, pi cube 3 cube, right? Pi to the 5th, x to the 5th over 5 factorial, and so on and so forth. Okay, it's not ideal, but it still gets you some reasonable answer. So then you would plug in this function with this function with this, remove the equality sign, and start replacing it with approximately equal to. So you would write A1 is approximately equal to 0 to 1. I have x over 2, 1 minus x squared over 8 plus x to the 4th over 192 times pi x minus pi cube x to the cube times 6 plus pi to the 5th x to the 5th over 120 and so on up to infinity dx. And then on the denominator I'll have 0 to 1 x squared over 4 1 minus x squared over 8 plus x to the 4th over 192 whole squared dx. But now you have so many terms, which is the new problem, but still not that bad a problem. We will write this is approximately 0 to 1 x or x over 2. I want to multiply these. What am I going to get? Pi x. That's the only first order term I'm going to get, correct? Pi x. If I multiply 1 with this and then x squared with this, I'm going to get minus x cubed times pi by 6 plus 1 over 8 times pi by 8. And then if I take this, if I take any other combination, I take x power 5, I take x squared and x cubed, it's all going to be higher order powers. Okay, so if I take this x to the fourth and x, even this is like x power 5. So I already have a x squared and a x to the fourth. I can make a justification saying any higher order power will only be less significant. So I will stop here. Now this integration isn't so bad. If it's like saying what is 0 to 1 x squared dx, which is 1/3, right? 1/3, and this is x to the fourth, 0 to 1 x to the fourth dx, which is 1/5. So I would have approximately pi by 2 times 1/3 minus 1/5 times pi by 6 plus pi by 8, which is pi by 24, no, 4 plus 3, 7 pi by 20. 7 pi by 24. You can get a number. At least you would have demonstrated your understanding of approximating it, convergence, and approximating it with a reasonable number of terms. This is what I expect you to do, not use your calculator. I want you to do something like this instead of relying on the machine. Okay? And in the denominator, what do we have going? I have x squared and then I have x to the fourth. If I do the square, this is only going to get smaller. So I'll even drop this from my approximation and write this is x squared over 4 minus, or x squared over 4 times 1 minus x squared over 4 times or plus x to the fourth over 64. I'll even drop this from my denominator. And when I further multiply x squared and x to the fourth, I don't care about higher powers. I'll again drop this. So I'll have in the denominator x squared over 4 minus x squared over 16. Sorry, x to the fourth over 16. So this is approximately 1/4 times 1/3 minus 1/16 times 1/5. So A1 would be approximately pi by 2 times 1/3 minus 1 by 5 times 7 pi by 24. The whole thing divided by 1/4 times 1/3 minus 1/16 times 1/5. Again, there won't be a direct question like this. When we do PDE, this will come up. Okay. So that is section 11.6. Okay, we talked about 11.1 and 11.2 and now 11.6. 11.9 is related to DFT. This is what the mini project is going to be about. So if you don't have access to a real-time signal from a instrument, voltage, velocity, mostly voltage, because most sensors output their output voltage. I can request Al Hassan to give you a sample signal, or if you have your own signal, which could be even computational data, you could use it. It has to be a time series, and you have to compute the DFT of your time series.
How many data?
Let's say you acquire about 1,000 values, a sequence of 1,000 values. What is the sampling rate so that we know what is the delta t and what is the function value for 1,000 values. So it's essentially like a time series, time in seconds or milliseconds, value of the function at that time. I equals 1 to 1,000. So you'll give like a 2-column data. So based on that DFT, you can make some comments or observations about the data. Maybe it has 2 principal frequencies. Maybe it has like a white noise kind of spectrum in which all frequencies are present in equal amplitude. You can make any observations that come from the data. Okay. You might be wanting to do like a frequency spectrum of your turbulence. You have a code that can give you any velocity fluctuations, something like that. If you share with the class, it will be interesting. Okay, so I have just a few minutes left. Maybe I'll just start PDEs from next week. Okay. So maybe after a couple of lectures, I'll share some sample projects, or I think maybe I've put some of the instructions already on Canvas. Kindly go through that. I really hope you would spend the month of November doing that project and make that presentation in the last 2 lectures. Okay. That is 20%. Just one presentation and the submission is going to decide 20%. So please take it very seriously. But I'll put a rubric that splits the score for choice of the problem. That is the kind of creativity you express in your problem selection, in your analysis, the actual calculations, your presentation, and the final submission that you do. You try to put a rubric for that. Okay. So please, this is the part where I want to take this course actually from math to a real analysis. So how you select the problem determines how much you can learn from this course. Of course, I'll share some examples. Thank you.